screen? Hopefully.
Yeah.
Perfect. Okay. So this was your summative on parts of the atom. It was about a week ago. So you guys, it said about how this lab, Argonon National Laboratory, announced the creation of xenon tetrafluoride in 1962. This was the first compound of xenon. The creation opened up an area of studying of chemical bonds. 3 chemists shared the success. So that was just the background information, just to give you guys a little bit more on this phenomenon than the 3 standards that were covered. Go into that in a second. So this, I'm going to go through by standards because that's how I graded it, and I think that might help a little bit. So standard 2.1. So this first question was the Lewis dot structures. I graded each of these. There were 7 total Lewis dot structures that went into your standard, or 7 total structures, 4 Lewis dot structures, tin. So remembering that they all have valence electrons is what I'm looking at. So tin has 4 valence electrons. So I was looking for 4 dots around tin. Xenon has 8 valence electrons. So I was looking for 8 valence electrons around xenon, or 8 dots around xenon, element symbol. Barium has 2 valence electrons. So I was looking for 2 dots around barium. And arsenic has 5 valence electrons. So I was looking for 5 dots around arsenic. So that's what I was looking for here. This one was also part of 2.1. What subatomic particle goes around the Lewis dot structures? And what I was looking for was that the Lewis dot structure, the valence electrons go around the Lewis dot structure, and they tell us the reactivity of that element. This one was a pretty good answer. And then the last one was a little bit farther down. This one right here, this was also part of 2.1, drawing the Bohr models. The Bohr models, I was looking for 3 things. I was looking for you to make sure that you had a nucleus, and that inside the nucleus you had your protons and your neutrons. And then around the nucleus, I was looking for all of the electrons on the correct levels. So potassium has 19 electrons, 19 protons, and 20 neutrons. It should have 4 orbitals. Xenon has 54 protons, 54 electrons, and 77 neutrons, and it should have 6 rings. And then fluorine or fluoride atom, this one has 9 protons, 9 electrons, and 10 neutrons. So that one, just drawing the Bohr models. If you guys have questions on any of those drawings and you want to go into further detail, let me know. But that was all 2.1. So if you got a 4, that's because you got everything correct. If you got a 3, you missed 1 Lewis dot structure. A 2, you missed 2 Lewis dot structures. A 1, you missed 3 Lewis dot structures. If you missed more than 3 Lewis dot structures or Bohr models, then you got a 0. 2.3 was the next standard. So this was the first question on 2.3. It said, what pattern did you notice within a given column of the periodic table? What do the groups and periods of that element, the elements belong to? Tell us about the element. So once 2 characteristics. Things I was looking for were you to tell me that if you look down the group, you learn about the number of valence electrons that the element has. Each group, the valence electron stays the same for that group or column. The period tells us the number of orbitals or the number of shells that go around the nucleus. So the first row or the first period has 1 orbital. The second row or second period has 2 orbitals, so on and so forth. There are other things. If you look down the groups, they have similar characteristics. They could tell us about the reactivity. They could tell us about if they're metals, non-metals. So just similar things throughout groups or columns is what I was looking for. You had to list 2 of them to get this answer correct. So the main reason I did see this answer being incorrect was because I only got 1 characteristic. So I was looking for those 2 characteristics. I'm going to skip over to this table real quick. So this table, you needed to determine if they were reactive or not reactive. You should have found that potassium and fluorine are reactive. Xenon is usually not very reactive. And that's because potassium has 1 valence electron. So it's easy to lose that valence electron to get its 8 valence electrons and be stable to be happy. Fluorine has 7 valence electrons, so it's super close to having 8, so it really wants that last electron so it can become stable or it can become happy. So it's going to be really reactive to try and get that 1 electron from somewhere. Xenon is not very reactive, or not usually not reactive at all, is because it has 8 valence electrons, so it's already stable. It doesn't want to give away its valence electrons. It's already got 8, so it doesn't need any more to be stable. It doesn't want to give any away to become stable. And that leads us into this next question, number 7, which is the last question on standard 2.3. And that says, using the periodic table as a model, explain why the creation of xenon tetrafluoride crystals were such a unique discovery. And that's just because xenon already has 8 valence electrons, so it's already stable. So making a bond, it's going to have to give away its electrons and become less stable. So it's not going to want to do that because it already has 8 valence electrons, or it's already stable. It fills its octet rule, so it doesn't want to do anymore. And then the last standard, 6.1, the first question was number 4 right here. Why are Lewis dot structures important when figuring out if an element will bond? And that's because of our octet rule again, because of having 8 valence electrons. All elements want to have 8 valence electrons to be stable. So if they don't, we look at the Lewis dot structure to determine if they're going to be reactive or if they're going to want to give away their electrons or take electrons. Question number 8. Why might scientists experience little success with creating compounds with neon? If we look at the periodic table, neon is right above xenon. It's one of those noble gases, which means it has 8 valence electrons. And it's already stable, so they're not going to make compounds with neon because it has 8 valence electrons, so it's already stable. And then the last one, which elements on the periodic table are the easiest to create compounds with? I accepted a lot of answers here. I accepted alkali metals, so anything in that first column, because they're super reactive. They have 1 valence electron that they want to get rid of. I accepted the halogens, or anything in group 17, because they have 7 valence electrons, and so they're really close to 8, so they want to get that 1 more so they can be reactive. Pretty much anything, if you explained it, I accepted, except for if you said the noble gases are group 18, so helium, neon, argon, krypton, xenon, radon. Those 6, if you put those 6 on there, I usually did not accept that because those are pretty much the only 6 that are not going to be easy to make compounds with. The rest of them, I accepted if you explained it. Usually what I was looking for were those group 1 or group 17 or group 2, any of those with little or a lot, not quite 8 valence electrons though. Does anybody have any questions about this summative? All right, so then what you guys need to do in order to retest, so there's going to be a retest available, is just make sure you have all of your assignments done for that unit. So in unit 1, under the periodic table, there were, I believe, there were 15 assignments between the start of our unit and the end of our unit. I do have a list if you want to contact me individually to see which assignments you're missing. As long as you have those assignments completed and you did them to the best of your ability, so you actually completed the assignment, it's not just turned in blank. I gave you credit for turning it in, and then I have a list of which assignments you've turned in. So if you're looking individually, send me a Canvas message, send me an email, let me know that you want to know which assignments you need to complete still for your retest. So you do need to reach out for that one. The last thing I want to do is I want to go through just the first page of our assignment for today. So today you have a 3-page assignment. And I just want to go through the first page with you guys. So if you guys can open up Canvas and go to the electron excitation POGL. It should look just like this. So open it up and it should look just like this one. So hopefully you guys opened it up and you're on this page as well. So I'm going to read the why together. So from fireworks to stars, the color of light is useful in finding out what's in matter. The emission of light by hydrogen and other atoms has played a key role in understanding the electronic structure of atoms. Trace materials such as evidence from a crime scene, lead in paint, or mercury in drinking water can be identified by heating or burning the material and examining the color of light given off in the form of bright line spectra. So question 1 says trace the arrows in model 1 and shade in the table with the colored pencils. So you guys can use your different colors. I'm just going to do 1 right here. So I'm just going to color in my first one. If you guys do that, I'm just not going to do that with you guys just because I want to go through that first page. But if you guys go through and you do all the colors and highlight or color in each of the table sections with the correct colors, I believe in all of your abilities to color, so we're not going to go through that together. But number 2 is where I want to start. Number 2 says, what happens to white light when it passes through the prism? So we're looking at this light bulb that says white light, and it goes through the prism. What do you see happen based off that picture?
The light reflects.
The light reflects, and it reflects into what?
Color.
All the colors. Perfect. So the white light reflects and turns into and shows all colors. So I don't know if you have done art and you've learned about coloring with art in terms of when you paint, when you mix all the colors together in art, what color do you usually get when you put a bunch of colors together with paint or markers? Or
Brown.
I did say that.
Brown, black, that like dark color. Well, it's actually going to be the opposite with light. So when we have light, our white light, when we put it through a prism, we can see that white light is made up of all of our colors. So every color imaginable, when you put them all together, if it's light, you're going to get a white light by the end. So that's why when you look, sometimes you see those rainbows coming out when you look through like windows, when it's raining kind of stuff, or when it's raining, you can see the rainbow. That's because white light, or the light we get from the sun, is going to turn into all the colors because white light's made up of all of our colors together. So now the question 3 says, why are the color labels in the table 1 in model 1? So this table up at the top, why are they plural? Why do we think these are going to be plural?
Because there are multiple colors of reds, depending on
Perfect.
what the light reflects.
Exactly. So they're different shades, different multiple colors or shades of red. Multiple shades. So multiple shades of each color. So we're going to see multiple shades of all the colors, which is why it says reds and not just red, because not all red looks the same. And then question 4, do all the colors of light travel at the same speed?
Yes.
Yes, they do. And bonus question, what speed do they travel at? Give you a hint. Look at the table. They're all going to travel at their speed of light, And since these are all lights, they're all traveling at the speed of light, and the speed of light is 3.00 times 10 to the 8th. So it's 3 and then 8 zeros afterwards. So it's a huge number, very fast speed. Number 5, do all colors of light have the same energy? So do all of our colors have the same energy? If it's a no, what color has the highest energy and what color has the lowest energy? If you want to send a chat, say yes or no. Who's got this answer?
Does red have the highest energy?
Which one?
Red.
Red have the highest energy, so let's look. So if we look at our energy level right here, red goes from 269 to 318 joules. If we go to the next one, orange, is that one larger or smaller than red? Or is it the same?
It's larger.
Is larger. Okay, what if we go to yellow? Is that going to be larger or smaller, the same as yellow, orange?
Larger.
All right, what about green?
Larger.
What about blue?
Larger.
Perfect, and then violet?
Largest.
Largest. All right, so we know that they don't have the same energy, not the same energy. We go from violets, have the largest. Reds are the smallest. All right. So now these key questions right here is number 6A through C. All right. So I want you guys to try and come up with 6A and B on your own. Take about a minute to answer 6A and 6B. 6A says which color has the largest wave or the longest wavelength. Which one has the shortest wavelength is B. And then we're going to answer C together. So on your own, take about a minute. All right. So can anybody tell me which color has the largest wavelength?
Red.
Red, perfect. We're looking right here at this section up here. Red had that largest number, so reds have the largest wavelength. Who has the smallest wavelength, the shortest wavelength? Which colors?
Violet.
Violet.
Mr. Zambelli,
What's up?
you're the shortest wavelength.
That's just mean, Oscar. Violets. Violets have the shortest wavelength. Perfect. All right. So now let's take a look at energy versus wavelength. Okay. So violets, they had the largest energy and they had the shortest wavelength. So, and then reds are the exact opposite. Reds have the longest wavelength, but they're the smallest amount of energy. So what do we think that means in terms of the relationship between energy and wavelength? What do we think that means in that relationship? If I had to make up some relationship between them, what do you think I'm going to say?
The color with higher energy has lower wavelengths.
Perfect. The color with the higher energy has a lower wavelength, and vice versa. If it has a lower energy, it's got a higher wavelength or longer wavelength. The color with the longer wavelength has less energy, and the color with more energy, or sorry, we'll just keep going with wavelength first, with a smaller wavelength has more energy. All right. Do you have any questions on anything from page 1? I'm going to take that silence as a no. So then you guys have the coloring up here to do, as well as pages 2. There are 4 questions on page 2, and then page 3. So going all the way to question 18. When you're done, you don't have to turn anything in today because we're going to do the rest of it on Monday. But so just finish up through question 18 today. The rest of it you guys should be able to do on your own. If you want to stay on and ask questions, that's up to you. Otherwise, you guys are good to go and have a wonderful weekend sitting and doing nothing apparently.
Bye.